Practice exam, problem 13, find the displacement field, the electric field, the polarization field, the potential, which is a scalar field, as well as the bound surface charge, the bound volume charge, and the capacitance for the system shown below, where the system is a conductor of radius A that holds charge Q, surrounded by a dielectric that is glopped on out to a radius of B, and the dielectric has a permittivity that is radius dependent, and so the permittivity changes as you get further away. So that's all fun and good, so let's get started. To do this, the first thing that we're going to notice is that we have a spherically symmetric system. As long as we have spherical symmetry, we can use the equivalent of Gauss's law for dielectrics, which is the divergence of the dielectric is equal to the free charge, or in the fundamental theorem when applied to that, right, the fundamental theorem for divergences, it says that the integral d2x over some closed surface, d2x of n hat dot d is equal to the charge enclosed, the free charge enclosed. Free charge for us is just the plus q, so we'll replace that. And then the final trick to realize is that we're going to say that because of the symmetry, this d of r has to be only in the r direction, like that. And I'm just going to even drop that r there. So it's just d is a function of r in the r hat. So evaluating that n hat is of course always going to be r hat for any spherical surface. So if we do a Gaussian sphere right there, for any spherical surface we draw, n hat is going to be r hat. And so this is going to give us 4 pi r squared, that's the surface area that we get from that d2x. N hat dot d is just going to give us this capital D of r. It's going to equal to our plus q that we get. Plugging that back in here, if we're inside the conductor we have 0 charge, and so we're going to get a piecewise function for d. D is going to be 0 if the radius is less than a, and it's simply going to be q over 2 pi r squared r hat if the radius is greater than a. And so the displacement field was rather trivial to find in this case. Now the next step is to find the electric field. Now the electric field, we'll have to go through a few different equations here. We know that the displacement field is equal to the epsilon naught, the electric field, plus the polarization, right? And the polarization is going to equal to epsilon naught chi, the electric susceptibility, times the electric field. Plugging that in, that gives that the displacement field is equal to epsilon naught times 1 plus chi e times the electric field. So the electric field will just divide by epsilon naught and divide by 1 plus chi e. Chi e is just kr, and so that's going to give us a piecewise function for the electric field. We're going to have 0 if r is less than a. We're going to have this q over 2 pi epsilon naught 1 over r squared 1 over 1 plus kr. And this is for a less than r less than b, and we're just going to have q over 2 pi epsilon naught 1 over r squared for r greater than b. And so that's not too bad. That was pretty easy to find. Similarly, using this equation here, that right there, we can immediately write down what the polarization is. And so the polarization field is going to be, we're going to get 0 if r is less than a or r is greater than b, and we're going to get simply epsilon naught times kr, and so this will give us q over 2 pi and kr over r squared 1 plus kr. And that's that. Now the final thing we're asked to find is the potential. Now the potential is the trickiest thing in here. And the potential, right, is given, in this case, minus the integral from infinity to whatever distance we're looking at a dl dot times always the electric field. Now, I guess I didn't write this down. This should have been in the r hat direction. That's in the r hat direction. And same with this guy. This is in the r hat direction. And this is, of course, for a less than r less than b. Since this should be path independent, it doesn't matter the path we take. The easiest path to take is, of course, a radial path inward, and then this dl.e will just give us explicitly what we want. And so this is going to give us then minus the integral from infinity to r of this expression. Now we have to do this in 3 different steps. So let r be greater than b, and then minus infinity, 0 to r, and then we have dr prime q over 2 pi epsilon naught 1 over r squared. And so for this first part, we're going to get the rather expected expression, right, of q over 2 pi epsilon naught 1 over r. Now let r let a be less than r be less than b. And the potential, right, can be broken apart into 2 parts. This will be minus the integral from negative infinity to b dr of e function of r, and then minus the integral from b to little r dr of this expression right here, which is q over 2 pi epsilon naught 1 over r squared 1 over 1 plus kr. Forget that one. And so we can just write this down. This isn't too bad, right? This is going to be equal to this first term, q over 2 pi epsilon naught 1 over b. That's this first term, factored out the q over 2 pi epsilon naught, and this will be then plus the integral from r to b dr over r squared 1 plus kr. Now I'm just going to go ahead and leave this in the integral form because I don't feel like evaluating that integral. But there's no difficulty in doing that in principle. It's just it's not a trivial integral, and so I'm not going to bother evaluating it. The final expression, right, if we let r be less than a, then we're going to get this same expression we had before. This v of r is going to be minus the integral from negative infinity to a dr times the e of r. That's what we did right there, but we evaluated at a. Oops, prime. And the next term would then be minus the integral from a to r dr e, and this is 0, right, because we're in there, so that part is just going to be 0. So this last part is just going to be the same thing that we have above, 2 pi epsilon naught 1 over b plus, and then the integral from a to b dr prime over r prime squared 1 plus kr. And so that's the expression that we have. So we can write this up. This is v as a function of r. It's going to equal 3 parts. First part is this. We're going to always have this q over 2 pi epsilon naught out front. And then we're going to get a 1 over b plus the integral from a to b dr prime 1 over r squared 1 plus prime squared kr prime. And then 1 over b plus the integral from r to b dr prime 1 over r squared 1 plus kr prime. And finally, we're just going to get 1 over r. And this is for r greater than b, for a less than b less than a less than r less than b, and then for r less than a. So there we go. So that's how we can do the potential. It's actually fairly simple. Now, we have now evaluated all of the fields that have been asked for. We asked to find the displacement field, the electric field, the polarization field, and the potential. And so the final thing that we're asked for, not the final, but the next two things, are the surface charge density and the volume charge density. And those aren't too bad, so we can just come here and write them down. The definition, right, we have surface charge density is n hat dot polarization field evaluated on the surface. So have to remember to evaluate this on the surface. And then the volume charge density is the divergence of the polarization field minus the divergence of the polarization field. And so we just need to evaluate these two. On the inner surface, okay, we have obviously, in this case, n hat is minus r hat, and on the outer surface, we have n hat is equal to plus r hat. And so we just need to evaluate, since the polarization vector we have right here is in the r hat direction, we just need to evaluate this on the inner surface, take a minus, on the outer surface, it's a plus. And so rho, the bound charge on the inner surface, we'll say that's at A, is going to be equal to minus Q over 2 pi Ka over A squared 1 plus Ka. And then on the outer surface, it's a plus Q over 2 pi Kb b squared 1 plus Kb. Now the gradient, in this case we do want to evaluate the gradient in polar coordinates, and so what we'll do here is we'll take this rho b is going to be equal to minus 1 over r squared partial with respect to r squared, and then the r component of this p vector, which is just this. And so this is q over 2 pi 1 over r squared kr over 1 plus kr. So the r squareds there are going to cancel, and then I just need to take the derivative of this expression. So when I write that out, my bound charge, the function of position, is going to be, of course I'm going to get 0 for r less than a, or r greater than b, because there's no dielectrics, therefore there can be no bound charge. And then in the middle I'm going to get minus q squared over 2 pi 1 over r squared, and then the derivative here. So the derivative on this can either hit the top, and if it hits the top we're just going to get k over 1 plus kr, and if it hits the bottom we're going to get minus, because it's something to the minus 1 power. The derivative is going to give us k squared r over 1 plus kr squared. Now we can simplify this a little by multiplying top and bottom by 1 plus kr. We see the second terms are going to cancel, so we're just going to get k over 1 plus kr quantity squared. So this is k over 1 plus kr quantity squared, and this is for a less than r less than b. And so there we go. That is the bound surface charge and the bound volume charge for the situation that we have here. And now the final thing that we're expected to find, right, is the capacitance. And the capacitance, switching colors yet again, the capacitance is just defined as the charge over the voltage for the system. Well, we have the voltage for the system at the conductor. That's this expression right up here. And so the charge divided by that, the charge is going to go away, and so the capacitance for us, capacitance is going to be 2 pi epsilon naught divided by quantity 1 over b plus the integral from a to b dr 1 over r squared 1 plus kr. And that is it. That was just a lot of things to ask for a fairly simple setup. And in this case, there was one non-trivial integral. I guarantee you on the actual exam, I will make sure that you don't have that. Just heads up. But even with it, it's not too hard to do. We just have to kind of run forward with an expression and an integral. It's not too difficult to ask. Okay, thank you.